This is the second project of Team 27. We built a quantum neural network for object recognition, more specifically for classification of deer in automobiles. We trained and tested our model with CIFAR-10 database. As you all know, deep learning based image recognition is a key technology for computer vision, artificial intelligence, autonomous vehicle, and urban surveillance. It gives the computer the ability to see, in particular for autonomous vehicles or self-driving cars, without the capacity to detect other automobiles, passerby, and possible obstacles. The safety of the passengers would be at jeopardy. Hence, quick and accurate image recognition is critical. To address this issue, we propose to expose the power of quantum deep learning and examine its performance in classifying and recognizing images of objects that can be seen on the road.
To implement this, we use this tutorial code page from TensorFlow for MNIST classification as our main reference. From here, we modify the dataset from MNIST to CIFAR-10, and we chose this dataset because it contains the most relevant images, such as different types of transportation and animals. From here, we additionally filtered images for automobiles and deer to reduce the size of data. Since the shape of the datasets are very different, with MNIST being 28 times 28 times 1 and CIFAR being 32 times 32 times 3, we had to edit almost every part of this code. However, the process of training and building the quantum model was similar. This is the Jupyter notebook that contains the whole code for this project. Firstly, we loaded the raw data from the CIFAR-10 dataset distributed with Keras. So we loaded the training examples, 50,000 training examples and 10,000 test examples. And then, like we said, we additionally filtered the data so it only contains the images of automobile and deer. This is the first example of the train sample. You can see the image of the automobile. Secondly, we downscaled the images because the image size of 32 times 32 is too large for current quantum computers. We resized it down to 4 times 4. After resizing, the automobile image shown here became like this. And then we removed the contradictory examples and converted the form of the data to NP.array. So we can encode the data as quantum circuits in the next section. Here we represented each pixel of the image, like each pixel square with a qubit, with the state depending on the value of the pixel. So we applied the X gate to each pixel that has a brightness that's higher than the threshold value of 0.5. So if you see the circuit, the X gate is applied to these 4 qubits because these 4 qubits correspond to each qubit, each pixel that has a higher brightness than 0.5. And then we built the model circuit for quantum neural network using this quantum circuit. We made a 2-layer model that encodes like where the data qubits act on a readout qubit on the top. This is the whole circuit. And we wrapped this model circuit with a Keras model. Then we trained and tested it. And after we trained and tested the model, we found out the accuracy of this model is very high, with 90%. To further improve this project, we can also train and test a classical model and compare it to the quantum model that we constructed. We can also try other data encoding methods and see if it enhances our model's accuracy. Furthermore, we can try training and testing with more types of data, since right now we've only used 2 types of them.